Hey everyone, in this video we'll go over LeetCode problem number 53, maximum subarray, and then in the follow-up video we'll go over LeetCode problem number 152, maximum product subarray, which is a nice continuation of this one. But for now, let's start by solving the maximum subarray problem. First, let's go over the problem description. Given an integer array nums, find the subarray of the largest sum and return its sum. So for example 1, we have the input array -2, 1, -3, 4, -1, 2, 1, -5, and 4. And we have the expected output of 6. We can find that the subarray with the sum of its values equals to 6 is from 4 to +1. Next, example 2, we only have one element. In that case, we just want to return the output 1. And for example 3, the input array has elements 5, 4, -1, 7, and 8, with the output expected of 24. And in this case, the subarray that sums up to 24 is all the elements in the input array nums. We will start by going over the naive solution, and then we will work from it to improve its time complexity. The naive solution, or we can also call it the brute force approach, is to go over all possible subarray combinations and keep track of the maximum sum across all of them. We can do that by using a nested loop and creating a variable to keep track of the max sum found so far. The outer loop index will mark the first element of the subarray, and the inner loop index will mark the last element in the subarray. For each iteration of the outer loop, we'll create a local variable for keeping track for the current subarray's sum, and it will be used for adding the elements in between the two indices. Then, we just have to check if the current subarray sum is greater than our global subarray max sum. If it is, we update the max sum. At the end of the nested loop execution, the global max sum variable will have the expected answer. So now we can look into the time complexity of the brute force implementation. The outer loop has a time complexity of O of n, and the inner loop also has a time complexity of O of n. Inside the inner loop, all operations are constant time complexity. So in that case, overall, our solution is of time complexity O of n squared. Even though the brute force solution works, it has a time complexity of polynomial time because of the nested loop. We can reduce the time complexity by implementing a solution using the sliding window technique. The main idea of the sliding window technique is to process data efficiently by focusing on a specific subset of the elements at a time and sliding that subset, or the window, across the entire data structure. The goal is to avoid nested loops, which can be computationally expensive, as we know from the brute force approach. The sliding window technique is easier explained using an example. So let's use the following example, this array with 1, 1, -3, 4, and 1. And we're going to keep track of two variables, max sum and current sum. The max sum will keep track of the max sum across all windows, or subarrays, and the current sum will keep track of the window's current sum of all its elements. The window is initially set to its first element of the array, and to represent the window, we're going to use two pointers, the start and end pointers pointing to the first element. Next, we process the current window. For that, we'll just set both current sum and max sum to the current value, since that's all we've seen so far. The next step is to expand the window by moving the end pointer one element to the right. The new value is another 1. We update the current sum by adding the new element. Notice that getting the current sum of the subarray is only constant time complexity, since we only need to update the current sum variable with the new current element, meaning we don't need to add up all the elements up to the end pointer. After updating the current sum, we can check if we should also update the max sum by checking if its value is less than the current sum's value. In that case it is, and we update the max sum. Again, we expand the window one more time by moving the end pointer one element. Notice that we always move exactly one element. Our new element is -3, and we add it to the current sum. Now the current sum is equal to -1, and then we check if we want to update the max sum. In this case, we do not because the max sum is greater than the current sum. After that, we expand the window one more time. Our new element is 4. This is an interesting case because notice that since we're looking for the max sum subarray, it is better not to include the negative sum of -1 of the previous window to our current element. Instead, it's better just to start the window from 4 and forget about the previous elements. We can do that by moving the start pointer to our current element. And we can update the current sum to the current element. Again, we check if we should also update the max sum so far. Since the current sum is greater than the max sum, we update the max sum. Finally, we expand our window one more time by moving the end pointer. Our new element is 1. We check if we should add the current element to the current sum by checking if the current element plus the current sum is greater than the current element by itself. In this case, we're checking if 4 plus 1 is greater than 1 by itself. So in this case, we add it to the sum. We also want to check if we should update the max sum. In this case, we do. If we try expanding the end pointer one more time, we're out of bounds and we know we're done. And the max sum will have our final answer, 5, which we got from the subarray that starts at 4 and ends at 1. Next, we can go over the implementation details, and after that, over the time complexity in more detail. So let's start implementing our solution. So for the first step, we want to initialize the two variables max sum and current sum. We will set both of them initially to the first element of the array, since that's the base case of the sliding window technique. Next, we want to implement a loop. The loop variable represents the end pointer of the sliding window, and we want to iterate from the second element all the way to the end of the array. We start by the second element because we already processed the first element when we initialize the max sum and current sum variables. Following the sliding window technique, the next step is to process the current window. For that, we want to check if we should either add the current element to the current sum or if we should move the start of the window to the current element. We can do that by checking if the current sum plus the current element is greater than the current element by itself. If it is, we don't want to move the start of the window and we want to add the current element to the current sum. And if the current sum plus the current element is not greater than the current element, we want to move the start of the window to the current element, shifting the start pointer to the current element. And we can do that by simply setting the current sum to the current element. But notice that this if statement can be simplified by just getting the max between the current sum plus the current element and the current element by itself. And then we also want to check if we should update the max sum. A simple way to do this is just by getting the max of the max sum and current sum. Finally, after the loop, we can just return the max sum, which will have our answer. Now that we have our solution implemented, we can go over its time complexity. As you can see, our solution is fairly straightforward. You only have one loop and it iterates through all the values of the array nums. And if we define n to be the length of the array nums, we have the big O of n for the loop. Inside the loop, we only have constant time complexity operations, and so the overall solution has linear time complexity. Comparing to the brute force approach, we reduce our time complexity from polynomial time to linear time by using the sliding window technique. For the last part of the video, I want to go over some signals in the problem description that you can look out for to consider if you should use the sliding window technique or not. The first signal is that you're dealing with sequential data structures. In this case, we're dealing with an array, but it could also be something like a string. Another signal that you should watch out for is that you're looking for a contiguous part of the data structure that is checking for some condition. In this problem description, it highlights that we're looking for the subarray and that you're looking for the largest sum. Other examples of this could be maximum product or minimum sum or any other condition that you could check for the subarray. And finally, the signal is not present in the problem description, but the brute force solution has some form of nested loop. And of course, not all problems that have these signals will be able to be solved using the sliding window technique, but it's still a good tool to consider when solving problems of this type.